track, there's almost no keeping track of the numerous exploits that are out there, and still there are lots of root exploits between them. Third point, root can also change the kernel. The kernel is the main operating program of your system, of your computer. So if you have a Unix operating system, then there's a kernel program. If you have a Windows operating system, there's a kernel program. It's the core of your system. We use it to do the things we want to do with computers. But forensics, as came up earlier today, also use that kernel to get all the information they want from the system. And root can change that kernel. And finally, the kernel, as in the forensics, but also in the period before that, in the emergency response phase, is critical to detect any abuse. Well, all these things put together make that kernel hacking and attack on a kernel is pretty effective. The results are pretty harsh if it's your system that's being attacked. Well, now, as I said, these are not new things. Everyone knows if someone roots your system, you're gone. It's bad luck, and try better next time. Rebuild the system. So if you're going to show how bad you can be if you can be root on the system, okay, we know that, so that's not an argument. So here are some counter arguments. Like, when you've rooted, you've lost anyway. My question is, why is it so easy? Why do I see a new Solaris version coming out and there are more such root programs, more root daemons running than were before? And why can't I do anything about it when I need those services? So there's no change in the way we use systems and build systems that make it less easy to get root. Kernel hacking is considered really sophisticated hacking. I mean that this is the elite, and okay, you're not worried about those guys because those are going to be in there anyway. You're more worried about the script kiddies because there are millions out there, and that risk is more considerable than the one of a sophisticated hacker targeting your system. Unfortunately, kernel hacking is scriptable. I mean, excuse me, that you can make a script with all the code, package it up, and send it to all the million script kiddies out there. And when it's easy enough for them to use it, they will use it. So it's not something that's so sophisticated. The first creation of such a thing is maybe a little bit more sophisticated than what an average script kiddie would do, but after that it's just the same. My operating system is closed source, so I'm much less vulnerable to it, or it's not even feasible to do it, because it's so hard to get into our system without knowing all the ins and outs. With Linux, on the other hand, or FreeBSD is much more vulnerable, so please buy our closed source system. It's complete bullshit. Why? Because what does an operating system vendor want is that all these people write software for them. They want device drivers written by third parties and not by themselves. They build their systems more and more in ways where it's easier to interact with it, where there's lots of information on how it works and how you can change their behavior. So it's not hard at all. And that's what this talk also will demonstrate. And then in the end, all the solutions are so hard to work with, because if you're going to talk in solutions later, you get all kinds of complicated systems with lots of administration, lots of rules, which are hard to maintain and maybe even don't make the system more secure. So my answer is, let's try and do better. With this presentation you will see what the risks are, what the effects are, and I hope it will motivate people in looking in more ways to solve the problem. But first, I want to talk a little bit about detection. In the end, that's the main issue here. It's not trying to break into a system. We go from the point where system has been broken. Someone rooted the system and then the important part for the person trying to protect the system is how do I detect that something is going on. So first of all, we look a little bit at detection. First, you have different types of detection. Host-based intrusion detection, which looks at all the files on the system, looks at the logs, looks at activity on the system, and tries to infer if there's any illegal things going on. And you have network-based intrusion detection, where you look at the network and try and see if there are any strange or anomalous or detectable abuse going on. If you look at the types of detection in both of these fields, you can make a subdivision and misuse detection, where someone is using an exploit that's known, and okay, if someone is trying to use something like this, then there's no other reason for it than being misused. There's anomaly detection, which is detecting anything that's deviates from what's normal, which you shouldn't expect in your network. And then there's general system health monitoring, which is not really geared to intrusion detection or detection of security incidents, but can really help such a process. And because it's also often the health of the system that's going down or changed when a system is under attack. Okay, and then there are different means to do detection. Systems are fitted on delivery with certain means, and there are certain parts that you can add to a system to make it easier to detect change. If we look at them, I have put up 4 major categories, but maybe there are a few others. Audit trails is all the things to do with logging what's happening on your system, and maybe parts that aren't allowed, so it can also be exceptions. System monitoring, which is all the tools that you use to see if your systems are up, what the load is on your systems. Integrity checking, which is checking that no parts of your system have been changed. If there's no violation of files, or mostly critical files, that you want to detect. And then there's the network protocol sniffing and reconstruction, where you monitor your network and try to infer from the traffic you see what happened afterwards. And you have all kinds of real-time, but also offline network intrusion detection systems working with them. So, if this is all the detection that's going on, what do we want to hide? Well, I can put up 2 hats. First one is the most obvious one. I want to hide my presence. On the contrary of all those script kiddies attacking all these systems and then installing their IRC daemon or whatever, real crime, in my opinion, especially in the future, will be perpetrated over a longer time in the system. The real crime and real hurt for companies will be if their networks are hacked and people have 3 months to get all the data out that they want. So to use a system without being detected over a longer period of time is very interesting. For a white hat, it might be interesting to hide your intrusion detection tools, for instance. Why should someone that enters your box see all the stuff that there's instead of just what you want them to see? And it's on the borderline of I won't say honeypot, but it's like a jail construction. Okay. What kind of tools are then used for detection on those systems? Well, Tripwire, I'm not sure if everyone is familiar, I suppose so. It's a tool that does integrity checking. More about it later, because I'll use it as a model of the class of tools that are easily subverted once you can change or modify a kernel. Process accounting has already been mentioned as something that's mostly standard on systems, but not turned on, but can be quite effective in tracing what happened on the system. Other kinds of auditing trail software, and of course the tools that come with an operating system itself, in the Unix world, NetStat or PS or whatever. So these are the products or the tools that you want to hide from. So what do you want to hide? When I break into a system, I don't want to be detected. What's the first thing that I think about? Any logs that I've created so far that are still on the systems, you want to change them. So that's easy. But next you want to set up something. You want to set up your backdoor. What's the backdoor? It's most likely a process or a modified process or file on the system which allows you to back in. So that will show up in the process list, or it will show up as a changed file, and you want that hidden. You want to hide that you are approaching the system over the network. So you want to hide all the network connections that are yours. You want to hide network connections for the backdoors that you left. You want to hide file modifications. We were talking earlier with the forensics on file modification as a great tool to track what someone has been doing on the system. And if you can modify a system so that the file times don't change when you do something, it's a good way to hide. In a little more detail, how you can fool a program, or we first need to look at what it does. Tripwire is an integrity checking program that works by baselining a system. It creates a database of what I call, what are called hashes, signatures, of all the properties of files on that system. So it takes file content, it takes file properties like the access times and the creation times. It takes directory properties and puts signatures on them and stores them in the database for later comparison. If I change a kernel so that the behavior changes depending on what Tripwire is trying to do, I can try and fool it. This is one of the most well-known examples of how kernel hacking has been used in the past. The trick is that for execution, you use another file than that's used for opening. So the file content is still the original one, but execution is redirected to your backdoor. So Tripwire will see the original with an open, and exec will call another one. So this is, in a nutshell, what modification of a kernel can do. I talked a few times about kernels, and okay, it's for some, I think it's daily work. For others, it might be very obscure what a kernel is and does, and what it is to your system. Like I said, in general, your computer comes with an operating system. That's a whole lot of stuff, programs, utilities, pretty pictures to make it look nice. But there's one core part, which is the kernel. And that's the program that's running from the start of turning your computer on until you shut it down. And this kernel offers all kinds of services to you. It allows you to use your computer. For instance, it creates new processes, so you can start new programs, which is pretty vital. It separates privileges and memory, so you can't go on and write in each other process memories where you don't have any privileges to. An example is, of course, you don't want to have any high privilege programs change behavior because someone else is writing. It also takes care of access of all the devices. It takes care of printing on your screen, and takes care of handling of the input of your keyboard. In generally, over time, these kernels have become very extensible. There are new developments that are that need fast incorporation into a kernel, and the kernel is structured in such a way that it can deal with it. So new network protocols or new types of file system can be brought into a kernel without changing the whole kernel by a certain structure. What is important, however, is that in most kernels, like in the normal default Unix kernels and in Windows, there aren't internal privilege levels. The kernel is the master in its own space, and it's the master that divides all the other privileges. So as soon as you run into the kernel space, you can get code running in that level, you are allowed to do anything. So what can a user do? A user can also inquire the kernel about the state. So how many processes are there? If there's something strange in your system, the first thing you do is type PS or go into your task manager and look what processes are running. At that time you are inquiring from the kernel its internal state, namely the process table, and report to you on it. You can also change kernel state if you want to change the state of a network device, if you want to put it up or down. If you have to require privileges that the kernel will check for you, you are allowed to change such kernel state. And of course you can also fork your own programs and processes, which is also a modification of kernel state. So how is this done? Mainly three ways. System calls, earlier someone shouted syscall table, that's involved in there. System calls are subroutine calls that you can use from your program to ask of the kernel a certain kind of service. Then there are devices. Devices are more used for things like moving data around. A system call is very direct with interaction with the kernel without too much data interaction. Device is more geared to large data interactions. For instance, def-kmem allows you to read all the kernel memory, or you have devices that are the disks, which also we're using the forensics example, where you can take all the data off the disk through a device. And finally, in the newer Unix versions, you see the proc the proc file system, which allows all kinds of low-level state interaction with the kernel.
Just one question
Sure.
about the proc file system. How is it handled by the kernel? Are every file watched every second, or I don't know? How is it working?
The question is how the proc file system is dealt with in the kernel. Basically, it's a special kind of file system, so it's really used as a file system. So you have open and close and read and write, and basically all the file system interface calls that you have for the normal file system also apply for this file system. Only what it does when it gets an open for instance, a file name that maps to a process can be that it opens a memory space instead of opening the file contents of the disk. So it's almost identical in the interface.
And for example, when I want to disable IP forwarding under Linux, I do an echo 0 in proxies net and a file.
Yeah, so what it actually does is does a write, it does an open of the file, gets a file handle, and does a write into that file. And internally in the kernel, that's called and mapped to whatever function you want to have.
The effect is immediate.
Yeah, because the open or the write call is a syscall. So in the end, it's a combination between system calls and devices in the form of file descriptors. And the write call is going into the kernel, and then the kernel catches it, recognizes what the file descriptor is about, and takes care of any action that it's supposed to do. It's a combination. Okay, so this is a talk about what the kernel does, how it interacts. Now we're going to look more at how do you modify a kernel? Well, as I said before, kernels have been more and more geared to third-party developers. Make it easy to integrate new stuff into it, make it modular. So one of the ways is loadable kernel modules. These are separate parts of code that can be dynamically loaded into the kernel, into a running program. So the program is on the fly while it's running modified. But it's not a prerequisite or something. It's not something that's necessary for you to be able to do kernel hacking. There are also other ways to get into the kernel space. In the end, the kernel memory is accessible through a device. So that means you can write directly into the kernel memory, which means you can even malloc a piece of code by just overwriting pointers in the kernel memory and simulating a real malloc in without actually executing it. And then use that piece of memory to put in your code and let some other pointers point to it. And then it's running in the kernel. Another one is build a new kernel executable. It's not the things that you hear about a lot, but it's pretty trivial and works a lot faster than trying to code all this stuff around it.
What's a fourth one that's patching kernels that exist on the disk?
Okay, another suggestion on modification is patching the kernel on the disk. And that's of course comes close to replacing it, but it's even easier because any difficult part with replacing a kernel with another one that you compiled is that you never know if all the features and stuff that was in the original one is also yours. So someone might see a system suddenly behaving differently because I had this strange option put into it. And you won't see that back in this precompiled kernel. If you patch an existing kernel on the disk, then chances are that you can preserve all the weird stuff that's in there and just patch the behavior that you want into it. So a little bit more about the modularization of the kernel. I said that it's more and more done. The reason is simple. You only use the resources that you really need instead of loading a kernel with all the options that a million customers might want. You tune the kernel to precisely your situation, and all the other stuff isn't loaded. It just stays on the disk. Modularization is in general for any design a good principle, and it isn't a flaw in the kernel or something that it's in there. But it's really easy to use and abuse. The mechanism how it works is normally you compile a program, you compile all the codes, you put it together, it might have shared libs somewhere else on the disk, and you run the program and it works. With the running kernel, there are some mechanisms where the symbols that are used in your code need to be resolved against the kernel. Then memory needs to be allocated in the kernel space, and then the code will be copied in. Most of this will be done by kernel functions that are present in the kernel. Okay. So, let's go. A little introduction on what this module that I wrote does. It demonstrates what can be done with kernel modifications. It does it on a Solaris machine, which I chose as my platform. One of the reasons is it isn't open source, but still there's so much info on it that it's not that hard to work without. Make it easy to use, because a lot of code out there and a lot of code examples out there aren't. That's why you don't see that much exploitation, in my opinion. Use of several ways to manipulate the kernel. The examples out there mainly focus on the system calls, intercepting the system calls in the syscall table. I use some other ways to intercept the data to show also that ways that you can invent to counter this problem shouldn't take this system call table as the place to protect and then you're safe, because that's something I've seen a little bit. Finally, it's open source, so anyone can use it and play with it and learn from it. A little part on the easy to use part and the fact that there's a lot of code out there that's not easy to use. First of all, there are some modules coming out now that are much better and easy to use. Another one is that in attacks on the internet already there have been cases where attacks with kernel modification have been seen. The most memorable for me that really showed how effective it can be is one that came up in a certain internet mapping or scanning project, I think half a year ago, maybe a year ago. And the team that did it described an attack that took less than 10 seconds on a Linux box. They didn't see anything of the exploit or anything of the installation, only because they were watching the system very, very carefully. Later, they discovered that the system was in fact hacked. Tripwire didn't see anything. All the system intrusion detection tools didn't see anything. So people are using these tools, and they are already automated to the level that someone can attack a system in less than 10 seconds. So if we are going to build such a tool in a little more detail, is okay, how are we going to proceed? The first thing is, I talked about earlier, think about how to fool programs. So what are the programs I want to evade, and how do they work? How do they get their data from the system? And on the other hand, look at the kernel itself. How does it work? How is it organized? And where can we intercept or modify the behavior so that we reach our goal? It's important to realize that not only is the kernel modularized, it's also using all kinds of extensible lists instead of fixed size or hard-coded properties and tables. The main things that are useful for modifying the kernel are switch tables, which are more or less just arrays with pointers to functions. So if I know the index, I can call a function for whatever function I need. So the system call table is such a function where exec has a number in the array, and if you index the array, you get the function pointer pointing to the exec function. So you can use this table to find the syscall you want. Other ones are linked lists, are used more and more because they are even more flexible. You can dynamically add entries to a linked list forever. And for instance, the process list on Solaris is a linked list. And there are global variables that are also very easy to find and modify. Okay, a quick example of how you can use such a switch table to modify its behavior. You simply take the value in the array, save it for use later, in this case old execv, and then write your new code, your new function called new execv, and put that into the place where the original value was. So what happens from then on, the kernel will always use this table for its dispatching of internal syscalls. So as soon as someone wants to execute a new function or a new program, my new execv is called. And of course I can then call the old one to be sure that the behavior doesn't change too much. If we look at linked lists, what can we do with that? linked lists are mostly double linked lists, so you can walk back and forth through the linked list. I can take an object that I want to hide and just cut it out from the linked list. Any traversal routines using the head or the tail and walking up and down that list won't find the module anymore, or whatever you're hiding. So, next is where do we want to intercept? Where do we want to start? What do we find important? First of all, we want to hide processes, so we look where can we find information on processes. There are two ways. The kernel memory is used mainly in older systems, but can still be used also in new systems to interrogate about processes. And the other one is the proc file system. If you want to hide backdoors in the file system, or hide backdoors is the talk that I just did with the modification of the pointer of exec_v. And if you want to hide files, you want to hide calls from the switch table that does all the file system access. And in this case, I've used the file system switch table for UFS file system. So that means that, first of all, that all the other file system behavior doesn't change, and that it's another place where the modifications have taken place. So it's not enough to check the integrity. You have a question?
Oh, I'm sorry. Yeah. On a operating system like a FreeBSD or something, will you compile the kernel with the proc file system? If you don't compile with that option, does that mean the attacker is only limited to looking at KMEM? If there is no proc file system mounted?
Yeah, of course. But that limits also the use of proc file system for any forensic or whatever detection purposes. So it means that some chunk of your code isn't needed in that kernel.
Okay.
Basically, these are the ways. What I'm looking at now is how do people find information, how do they look for information if they want to detect an intrusion. Well, one of the ways is through proc. If there is no proc, then it's def kmem mostly.
So you think the benefits of keeping proc mounted outweigh the benefit of eliminating it?
From this point of view, it doesn't matter much.
Okay.
The only thing that depends is how much effort someone put into writing a modification. Because if you went through the effort to make sure that both ways of looking at the system are changed, then you won't see anything different.
Oh, okay.
And if proc would introduce any vulnerabilities or risks through another way, then that might be a reason to not do it.
Okay.
So, but because I went from the Solaris system where proc is default there, that's the reason why it's here. It's even so that quite some utilities don't use the KMEM interface anymore, but you can still write programs that do it. So that's the reason why you want to block both ways of looking at the system. Okay, I was on the UFS switch table. The thing is that there are two places where you modify something, and that something that tries to control or check the integrity of your system has to look at a whole lot of places if you want to cover all the places that you can change in the kernel. Okay, this is a little bit of code just to show what it looks like in a C code. You just have a number defined, which is an entry in the syscall table, and the syscall itself has a prototype of how you are supposed to call it. So your new function must precisely do the same that the old function did, and get its arguments in this way, and then you can modify them and work with it. So, for this example, the example is just about exec_v. There are like, well, maybe 10 or 15 places where similar modifications are made in the kernel in this program. Exec_v is just the simplest and used as an example. As I said, first what you do is you save the original, replace it with your new pointer. do your work, whatever. For example, people check what is the executable that's being called. Is it one of the ones that I want to backdoor, yes or no, and then call the old exec if it's not the case, or do something else if it's the case. The advantage of using the old exec-e is that you don't need any knowledge of that internals. So you don't need to modify any internal code of Solaris to do what you want to do. The only thing is you overlay the function that's already there with some additional modifications that you have, and which can be some precondition checking. Are you in a hidden state or not? Are you the attacker or are you the administrator? And do whatever you want. Also, if the kernel is patched later and the modification, the behavior changes, bugs are fixed, by keeping calling the old exec function, you also benefit from all these patches. If you would hard code a whole new exec-e, you would be stuck with all the bad bugs, and someone that's patching the system would immediately see that there's no change, for instance. Okay, so what is the behavior that we want from our new exec-e? Test if there's a backdoor executable being called. If not, throw it through. If so, we want to redirect the exec to a new program, the one with the backdoor code in it, and also try and make it as invisible as possible from username. I think now there's all kinds of code coming, well, not so interesting. You can look through it. It's just some checking and showing how little code really is needed to introduce such a modification. So the result is if we have configured the module with a backdoor file name of bin login, as soon as exec-v is called, it's going to test. It sees, okay, this is our backdoor, and what it will really do is call another file that I also configured. So in this case, maybe bin my login, but it can also in my secret stash slash login. But when I do an open bin login, I still get open bin login. There's no modification in the open call. So Tripwire will still see the content of the old one. So to give you an idea of what has been involved in the coding and how much has been changed, these were all the system calls that I changed. Fork 1, I'm not even sure anymore what the difference was, something to do with the vfork. Kill and SIGQ are used to send signals to processors. At one point, Thomas Potacek, he proposed a method to find hidden processes by sending kill signals to all the process IDs that you can enumerate. And a hidden process shouldn't give any results back. So the kill system call should give an error message if there's no process, and also if there's a hidden process. So a little modification to those system calls made sure that that's happening. And then of course the exec-e for redirection. For a file system, there are quite a lot. There's two reasons. The proc is also a file system, so any process hiding in the proc file system is also done through file system routines, notably the PR, redir, and lookup. And UFS calls, there are a lot more. Why? Because I also introduced need some water. It's because I also introduced a booting feature where the module will stay resident after booting. This requires some file system changes and modifications that you want to hide. And that's why you have all these rename and create and remove calls in there, because they need to work around this hidden file. And the spec IOCTL, let me think. I think it's mostly used for catching another way to interact with the module. Because this module is going to run in kernel space, you want to configure it from user land. So you have the same problem as the kernel has. You want to talk as a user to your kernel modification part. You want to say what's the new backdoor, or you want to say hi, this network connection. There are two ways to do it. One is through system calls, so you intercept another system call. Another way is through an IOCTL on the device, which is one I chose. Okay, so then we have left Cayman, read, and netstat. I think for netstat, in the end, netstat is the problem showing the network connections. In the end, there was only one of those two needed. So, a whole bunch. So, these are the system calls that are used. So now more about, okay, what are they used for? What are the features? What does this code do? First of all, it hides processes. This means that if I'm an ordinary user or even root, but not in a special state, I can't see processes with a certain hidden flag. In the kernel, a lot of things are done by putting flag bits on to show the state of a process or a file or whatever. Generally, these are integers or longs or long longs. So there's a whole range of bits, and people use up the bits as they go by. This means in generally that there are unused bits in every status flag or whatever used in the kernel, which is really handy because you can attach your own bits to it. So what I did is I created a new flag bit in the process structure that says I'm a hidden process. And this process will carry this bit with it. All the things are set for it to keep that flag with it. And it's a really handy way to test all out over the other code if I'm in a hidden process or not, for instance, so that the hidden process can see a whole lot and the unhidden process can't see anything. Fork will spawn off a new process, but because of the flag, it can test on the flag. So fork has been modified to test on the flag, and if the flag is set, make sure that the child process has also got the flag. So if I'm in a hidden shell, all my commandos, all my commands and all the processes I spawn are hidden too, which is nice because you don't need to keep track of all these processes you're generating and if they're hidden or not. As I said, signals to the hidden process fail. Information on network objects. A bit of a strange way to talk about network objects, but basically, if you do netstat and you have a line saying listening on port this or that, or there's a connection between this computer and that computer on that port, those can be hidden on port number. In the file system, basically you want to have some place where you can store your stuff, if only the module itself and the things that you enter. But most of the time you want to store more on the system. So you want that not only files are hidden, but also directories with the complete contents are hidden. This is getting worse and worse. Let's see if I okay. So what we do is we use a prefix, simple string, user configurable. As soon as it's prepended to a directory name or a file name, that file won't show up. Okay. For directories, if there are hidden files in directories, you need to modify stat. And finally, the system is reboot proof. Oh. So, I hope I'll survive this. How does the reboot-proof mechanism work? Simply said, the kernel is built of a whole lot of modules that come with the system. So there is a very modular operating system and kernel. So, what's easier than to modify one of those modules or replace it where you know that that module is going to be loaded on booting. So, in this case, I took conld. I'm not even sure what it does. A slight typo. This is not shouldn't be missed, but also struml. Anyway, you move it to a file with a prefix that's hidden. So, from that moment on, that file is no longer visible. And then you put your own module in its place. So, as soon as the system boots, the kernel, the modification or of the kernel is not yet installed. And conld will be loaded into the system, but it's my module. At that moment, the first thing it will do is reload the original by calling prefix and loading that module into the kernel. So the conld is actually loaded, but only after my module has been loaded. Then it swaps some stuff around on the file system so that you don't see that the conld does have different file properties from the original conld. Which is of course important, else Tripwire would have found it in no time. Okay, this is a good thing because I need a demonstration. Get my fuzz back. What I'm going to do is, I have a box here on the floor. This is Solaris 2.7 box. From this laptop here, which is a Linux box, I'm going to hack root remotely with a well-known exploit, nothing new. I'm using the CMSD, it's a calendar manager tool on the Solaris box. I will install the kit, install a vector on the system. I'll first run Tripwire to see that the system is clean. and afterwards to show that Tripwire still thinks it's clean. Show you a little bit on what it can hide and what it can not hide. Then I'll reboot the box to show the reboot trick. Go on a little bit into the counter attacks that you can have against such modules. Okay. First, I need something stronger. That's out. Okay. Okay, so I'm going to do a whole lot of switching between screens, and I'm going to be as clear as I can about what system I actually am doing what, because it can be a bit vague. Actually, this is on the system. First of all, let's show that Tripwire, the things Tripwire is checking is mainly only the critical parts that I'm changing. Oops. I'll put it down a little bit more. Okay. The exploit. What else? Exploit. Okay, what it does is install a backdoor. This is all the normal stuff. Nothing's running. Now I'm going to attack. Oops. It's all pretty lame backdoor stuff. It needs a semicolon on the end, and it's terrible. Normally, this would be a very nice encrypted backdoor login, of course. To show that we are now on the victim root, I'll go to temp directory and get the tick, the kit from the attacker. Okay. Kmod kit.tar, easily packaged in a binary kit. So what do we have here? This is the outcome of the Kmod source code. You compile a pre-compiled binary kit. It has two scripts, of which the important one here is install -perm, which is a permanent installation on this system. All I need to do is install perm. Okay. It's installing itself in etc scal, but I don't see it, which is good because I'm not in a hidden state. To be able to access all the stuff that's hidden, you have to be hidden yourself. So first let's find out. There's a mod CTL mod control tool where I now say hide myself. $$ is my own process ID, so I'm now hiding my own process ID. And now I see there a directory has appeared called hide me. If you now go back already at this moment to tripwire, although in etc scal and in the kernel module directory there have been changes, everything is well. Really no violations yet. Also, my process ID is 360. Oops. It's not there. So, from this moment on, all my comments will be hidden already. And the files are hidden already. What we also can do is the backdoor is 354. That's still visible. No, it isn't. So everything I installed now is invisible. I have my secret stash in Cal. Slash high. And what we see there are some tools that are, there are 3 files .attr, which are the attributes that are saved. They are the original file stems and properties of the files that are changed. So we can always reset them, and that's used to, among other things, full tripwire, because we can change files as long as we can put back all the properties that were there previously. Login is the backdoor for the login program. Do it is a script that will be started on reboot. You can look at it. What it's doing is it starts the backdoor. It's already stated. It hides the network connection 1880, and it installs the backdoor hide me login for the original user bin login. What I can show you is netstat. Which is showing the connection that we'd expect. I'm telling it into the system on this screen, and I'm connected to port 8080 through this backdoor. On this side of the, it's also still visible. Maybe I should do something like. Make it a little bit more clear. Now I'm hiding all the internet connections dealing with port 8080. So from now on, the network connection is gone too. And it's also, if I do A, then it will show all the listening ports. Is also gone. So, all in all, not much detection going on yet, especially in light of the fact that the exploit uses a hole that doesn't leave any or hardly any logs. So the daemon that had vulnerability doesn't report I've been rooted or something to the log files. It just dies, or maybe leaves a log saying that it died. Most probably not. So, any ideas on ways that we might detect some of the stuff that's now installed?
Does Solaris allocate process ID randomly or linearly?
Linearly.
So will you see big gaps in your process numbers? Like, you know, as it's allocating processes as the system starts up, there'll be a big gap in numbers right at the beginning numbers.
There will be a big gap if you run a lot of things.
Oh, okay.
The trick is that the backdoor is executing the do it program, but it's only doing it after a time delay.
Oh, okay.
So that's a configure delay. I'm not sure what it's set at, but you can set it whatever you want. So you have a window where your stuff is out there, at least for part, because the module itself has to be loaded, but the backdoor has to be installed, etc.
Oh, okay.
But you can detect it with a port scan if you compare it with your netstat output.
Yes, you can. Only if you're in the kernel, you don't have. You shouldn't underestimate the things that you can do.
But if you do a port scan from the
if you go back to this system, and you still see the ports out.
Yeah.
That's
You
correct.
could always modify it so that it only subject matter
Sure, this is only because I didn't write anything that does it better. It's fairly easy if you take like IP filter toolkit, modify that a little bit to only allow from a certain source, like you have in filter rules. You can make it look like that it's always sending resets only if you are coming from a certain source or port or with an IP ID of a certain value, whatever.
What about shared memory segments and allocated memory? If you take a look at memory that's allocated to processes and you find chunks of memory that have not been allocated to processes in your processes.
Okay, so the question is, what about memory management and memory allocation? I have to say, let me finish this off. I'm not too familiar with all the ways that you can use on Solaris to interact with the system. Like, like something like VM stat or something.
I don't know anything about Solaris,
Oh.
so, but there is a way to keep track of allocated memory. So I suppose you can just check if there's memory allocated, but not allocated to any known processes.
Well, the problem is most of the time is in what direction can you search. For instance, there's a lot of information is only one way. You need process structure to figure out where all the things are going. And it's not easy to go, for instance, in Solaris, from a port to a program that's using it by following the structures internally back to the program. All the matching that you do now is look at all the processes and look at all the ports that are open and grab your port from it. But there's hardly a way to get from a TCP or a UP string back to the process that's using it. So there are a lot of one-way structures in the kernel. So it's not always so easy to come up with ways to find hidden processes. So I'm not sure how that's done with VM management.
Yeah.
In the back.
I mean, another option, accepting that you're totally screwed when you're kernel integrity got gone to pot. I guess the other option is to do sort of passive analysis of network traffic and say, okay, it doesn't detect that your kernel necessarily being routed, but you can say if if you're detecting traffic on a port which is not represented in the next output, you correlate the two, even though there's certain tricky things for doing that properly. You could then say, okay, there's a mismatch, and therefore we've got an activity that's not explained by the system.
Okay. The remark, more or less, is that there's a way to detect this from external passive analysis. If you look at the network traffic to this machine, you'll see all the port 8080 traffic going on, and from that you can infer that there's something going on in that machine, although you can't see it locally.
I would say that's incorrect though, because if you're going to install a backdoor, you're going to use both the port number that's already being used, but also protocol using something like, well, HTTP tunnel or something where it actually looks like valid HTTP traffic to the web.
Okay, that's a good point, and it's also tying in with something that's on a later sheet. The remark is that if you're going to do anything stealthy, then you'll be using well-known ports or well-used ports for your stuff so that it doesn't show up in all the traffic. And one of the interesting combinations with the remark on being able to scan a port or make it look like it's closed is using something like IP filter and intercept your traffic based on some token, like a source address, and internally in the kernel, redirect it to another process. So, or even to another local port, like I have my backdoor listening on the loopback interface from port 83000, and it's accepting HTTP traffic, which is being redirected by this IP filter module, which is taking all the port 80 traffic, which is not from the source address, and directing it to the normal HTTP server, and only redirecting all the port 80 traffic for my backdoor, because it's from my source address, to the high port of my local backdoor. And then you have the problem of trying to infer from HTTP traffic without knowing what's on the website, because intrusion detection software doesn't know what's on the website, to try and see what's valid HTTP traffic and what's not. And then it begins to get quite difficult.
What about CPU usage?
Okay. I guess you mean CPU usage and in how far can you detect that such a module is installed, for instance, or would the load be higher, for instance. It is an issue, but it's hard to baseline it. How are you going to say if it's not noticeably slower? So you would have to have it from statistical analysis or something to see that a directory listing with, which contains hidden files is taking longer. It's taking longer than would have on a system without them.
Yeah, performance tools can, for example, glance can allow you to look at the list of processes and then the usage CPU, and you can see what's going on.
Of course, there are a few more cycles used. That's for sure. I'm not so sure in how easy it is to detect it, because you need to baseline something on a system that's known to be secure, and then try to correlate that against a hacked system. And I'm not sure if that's easy to do.
Could you have a tool that baselines the kernel structure and then check later on that it's been modified by your
Okay, the question is, can you somehow do some kind of integrity checking on your kernel? It's an issue I'm coming to later on the other sheet. Basically, it's pretty hard, I think. Especially if you look at how many places you can change. One of the most important prerequisites for it is a trusted boot. You need to be able to have the kernel come up into a certain mode that you can completely trust, and no one can change, even root can't change. So, and then you're already in the process of introducing something like secure levels or something like a root with not completely root powers, because you can do everything except for that. So,
I think at the end of the day, even going to the CPU usage example, a lot of that stuff nowadays is still done, is now being done through the proc file system. And I firmly believe that if you go rid of the box in this way, that there is no way that you can actually say that you can detect it from the command line of that same box, because everything could be trojanized. Absolutely.
yeah, that's true. In the end, it's who gets there first. And if you can come up with something, a way to check it, but I'm before you, I can come up with a way to circumvent it.
What about used disk space? I mean, if you do like a DF or something and you DU, I mean.
Okay, DU I can show you.
They always have to consult the kernel though to actually get that kind of information. And if you've got code in there to intercept those calls.
Well, but if you have like a statically linked DU or something that's not dependent, right?
You're trying to detect free space on the disk.
Right, yeah, and compare it against.
But I say the DU program actually hooks into to the kernel file system to actually get that information.
Yeah, okay.
So all you need to do is add on or take away.
No, you'd have to DD the whole drive, take it to another machine, and analyze it there. Yeah.
Hey, very good.
Yeah.
And there are even answers to that. Even if you're going to look at forensics and ways to circumvent that, because this is also one of the reasons I'm talking about this and doing this, is it forces you to think further. What I would do if I knew that forensics is also an issue is install a completely separate file system, encrypted file system, into a hole in the original file system, which is completely separate. So no one knows beforehand that file system is in there, and because it's encrypted, it won't show easily up in any forensic tools. And then the other part is setting up, and in Solaris there are also provisions for that, a separate scheduler for your hidden processes. So your processes aren't on the list of the original processes at all. And all the tools that you use to look at processes just see the complete list that is in the kernel. And that would really make it a next step harder to detect something like this.
What about booting from a CD, for instance, and running Bitwire from there? Then you don't have the same kernel.
If you have an option of booting off something else before running Tripwire, that's a good option. Because in the end, all goes wrong because the program is telling something different. If you do a DD and go analyze it, you also find all kinds of stuff. Also, a good option that's been briefly mentioned this morning is the possibility to core dump the operating system, the kernel, which freezes all the information in the kernel. Okay, it does it in the swap drive at this moment, but it allows you to walk all the stuff in the kernel and also find things like an encrypted file system module or anything else. So those are the best ways to look at a system when it's been compromised like this.
All those do involve taking down the system though in the first place, doesn't it? All those dumped in the kernel and also running off CD. I mean, how regularly would you read the impact on CD? Because you've just done that exploit there and trojanized the system, so we might not find out anything.
Yeah, because even DD, because that's one I maybe forgot, is modify the raw device. Make sure that all your stuff is not outputted to the raw device. Then your DD doesn't work anymore either.
Then the question is, do you regularly you do a DD because you might suspect something's wrong? You do these things when you have some knowledge that something's wrong with the system, and if things don't show up in the first run, then you have no knowledge, so you won't do a DD or boot from CD or
on your clustered server.
And generally, you want to make sure that no.
You go to your management, you have an Amazon web server, you say, well, boot from CD.
Yeah.
Okay. I see one question. Then I'll go on. Finish on the sheet because we're now talking about all kinds of stuff that's still in the sheet. So.
Strings provide the links to the vector change kernel. I mail myself the strings from yesterday and the strings from today. Have the diff running against them, and if there's a difference, I know, okay, there are new strings in the kernel, something's moved.
How do you run strings on the kernel?
On the executable?
Yeah, and how do you know what data is coming back? Okay, I'll first reboot the box now so we can show later if it works. Okay, well, let me first proceed with some remarks and ideas on what to do about it. I hope my voice recovered a little bit. So the next thing is, okay, what can you come up with for new ideas of making it even more difficult? So we talked a little bit about it already. The first thing is, okay, there's no loadable module support, or just don't use the loadable module facility and just copy it directly into the kernel, which can make it for some ideas of detection, make it hard to detect, because some talk about limiting the loadable module interface, etc., etc. So copying directly into kernel has been shown. There's example code out there. I think it was for Linux. In kernel network daemons, or daemons that are listening on our ports with some form of advanced redirection, like we just talked about with a backdoor in your HTTP server. Modify the executable code of the kernel. I'm not talking about loading a kernel module, but actually modifying the executable part of the kernel. Most of the time this is protected by the memory protection in the system. But for Linux it has been shown that you can patch executable code in the kernel. And what does it allow you to do is you don't change the system call table, which is like a variable, but you patch the first instructions of the exit vehicle to jump to your routine. So the syscall table doesn't change, but the executable code is changing, which also makes the space that you got to cover to find all the places that can be modified even greater. A suggestion which was made in the FRAC was to flip some bits on the TCP protocol. So if you do it at both ends, I can have a perfectly working TCP connection with a SYN, SYNAC, and a fin at the end. But on the network, I see push UCK, unknown flag, and that's because there was some flipping used in the network stack on both ends, on the attacker system and in the kernel modification. What does it do? Intrusion detection doesn't see a valid TCP connection anymore. If you have anomaly detection, you might see this. But if you have normal intrusion detection that's looking for strings in TCP connections, they won't be able to make anything of it and just disregard it. Some other stuff, snooping TTYs. We've been talking about tapping or interception by law enforcement. Snooping T2Is is a really effective way to see what's going on in the system of administrator working. You can easily do it in a kernel because everything is passing anyway. Okay, this is the thing with the token. Okay, what can be done about it? As I said in the first slide, or one of the first slides, the issue is that root is almighty, and that root is allowed to change the kernel, and a whole lot more, and that it's easy to hack root on a lot of systems. So what you want to have are means to reduce this exposure, to reduce the rights that root has, the ability that he has in the system, and to reduce, of course, the opportunities that there are to hack root in the first place. If we look at reducing the power of root, the first that comes to mind is secure level implementation. I'll talk a little bit more about it later. It's a rather black and white division between what is still allowed and what isn't anymore. You can have some more fine-grained controls where you allow very specific privileges for very specific tasks with very specific roles or people on the system, which is generally referred to with secure operating systems. You can have a user-land kernel integrity checker. Well, as we've shown, it's easily fooled if you're depending on what the kernel tells you. How will you ever know if he's not telling lying to you or fooling you? So trying to make a hash of the syscall table and checking that regularly doesn't work if you change other parts of the system. In kernel integrity checkers. That's a little bit more useful. Why? It's more the chicken and egg problem. If I'm there first with my checker, it can be made pretty hard to get back in there. It can still be done, but it covers a whole lot of ways in. On the other hand, if I already am in there, or I can intercept in the boot process and insert myself before the checker is loaded, then it's lost. An example of this kind of software is the integrity protection driver, I think it's called, for Windows in this case, but it's still software. So secure levels, what does it do, how does it work? It's basically just a flag in the kernel that says I'm at this level, and that means that root isn't allowed to do a couple of things anymore. For instance, root isn't allowed to change immutable files anymore. And immutable file is just another property, it's just another flag on the file in question. Or it's not allowed to write or in kernel memory anymore, or introduce new kernel modules in the system anymore. And basically it puts a blockades in all the means that I've been showing where you can easily introduce code into a kernel. It's mostly found in BSD Unix, and in Linux has had some form of implementation, but I don't think it ever took off. Because it's fairly hard to do well, because you need to implement it all over the kernel, make sure there are no ways around your checks, make sure there are no ways to flip the bit that says you're in secure level mode due to some programming mistake or whatever. You don't find it in most of the commercial Unisys. More fine-grained privilege systems, they generally tend towards the more academic type or defense type of systems, trusted operating systems. The main features are the capability model, which says is like a whole database with privileges and capabilities of programs, what they are allowed to do. Linux has got an implementation. I'm not sure if this still is a valid link, because I'm not following Linux that closely. But this is the way that Linux chose to go away from the secure level, which is black and white. You either are allowed to do everything, or you're not allowed to do anything with root. This tries to find a way in between. But the contrary part of it is it introduces much more maintenance. Because you have to say what all the capabilities are, who has what capabilities. Then there's mandatory access control, which is a kind of a labeling system. Things from the network, objects in the file system have labels, and rules apply on which may interact. There's also a Linux implementation, LOMAC. Trusted BSD has some information on it and some example code. Again, it's the same thing also used in things like Trusted Solaris, which is a full trusted operating system with all the bells and whistles that come with it. The general problem with these systems that are found is that they are so complex to manage and that the option or combinations of features are so diverse that no one can understand what's happening anymore on your system. So it's very hard to see if you made a configuration mistake and what actually happened. I heard from Pitbull, the guy from Argus Systems. They had a system up at DEF CON, and the night before they put it up, they found a configuration problem in their own setup. So these are guys building these systems, and even they find on a night when they're going to put it out in front of a lot of hackers, find out that they made a configuration mistake. Well, if they find out in such a moment still that they made mistakes, it gives you an idea of how difficult they are to maintain. Something slightly more new.
Yay! I like jail.
Okay, a jail fan.
Yes.
I haven't done much with it, but I think it's a very nice idea, and it shows a little bit the direction in which solutions should be solved. It's basically, like it says, Paul Henning's own words, beefed up JRoot. JRoot was more or less a file system type jail. It didn't have anything to do with network or processes, but it limited you. There we go again. It limits you to a certain part of the file system and doesn't let you out anymore. What Jill does is do the same thing, but also for processes and also for network access. So it leans towards small virtual machines within one machine. And basically, what you can do is give someone root in jail, and he's only allowed to do all this stuff inside the jail, but never can break out of it. So you can never touch your main system as root. So it isn't allowed to load kernel modules, isn't allowed to change all kinds of things in raw devices, etc., to make it more secure, but at the same time more usable, because the whole configuration that's needed for this jail system is a whole lot simpler than what you have for a full-blown trusted operating system. Well, as I said, Windows has the same problems. Internals are less understood, at least by me, yet. There's an open source project called the Rootkit project, among others by Greg Oakland, who couldn't be here apparently. They've been showing the same kind of things, demonstration code for such attacks coming out. There's one too many. How do I do that?
Up. Yeah.
Oh yeah, I didn't want to forget it. I use Tripwire as a demonstration tool. It's a model for all the integrity checking software and problems that are tied with it in regard to the kernel integrity. It doesn't mean that Tripwire software is useless or something. I think it's a very useful product. And I want to thank Gene Kim for giving me a copy to demonstrate here today. I've some references. The Hacker's Choice is one of the groups that put out quite some example code on kernel hacking with quite some explanation with it to show the problem. Also, good Unix internal boots are not bad to use. You play with it. And finally, there's a link where you can find the code for the module. Okay, now I want to go back to the demo for a small part. Okay, let's see if we can still get back in. Oh, always. Okay, so apparently the backdoor was installed after booting. Another way to check if the system has been compromised is now it shows a banner. This is a backdoor login. So what I did was just code a little routine around the original login. So it's calling the normal login afterwards, just to print the banner. Oh, no file. To show that Tripwire is not running with an empty database, which would have worked fine for the demonstration so far. I will go to so we're now going to hide process 297, which is that shell. And when I'm now using Tripwire to check, it's running in a hidden mode, so it should find and it's finding both a new directory and a changed module. Okay, any questions?
Just a couple of comments. You explained that that whole thing is depending on two prerequisites. One is the almighty power of root on conventional systems, and you were explaining some alternatives to that. The other prerequisite is that there is a root exploit that can be used to get in, and there also are a couple of things to protect from this side. I mean, most of the root exploits are based on buffer overrun attacks, and there are some known technologies to avoid that. Not on commercial systems, I have to admit. The other comment is, I don't agree with your statement that your trusted operating systems as such are too complicated to administer and to run. There are some commercial versions of simplified trusted systems available that can be used by their standard operators and administrators.
Okay. Especially in the last comment I'll repeat about trusted operating systems being complicated. The remark is that there are simplified versions out there that are more usable or very usable by normal administrators also, and help a long way. The other remark is that preventing people to get root by all kinds of root exploits is also an important step. And I agree, I wanted to say about that is also for Solaris, but for a lot of operating systems these days, there are so-called hardening tools available. For Solaris, there's just a third, developed even by some, which will turn down your system, remove all the unnecessary such as root programs, etc., which is for every production environment something that should first be done before doing anything else, I guess. So that should limit the potential root exploits for a large part.
Now, just to ask the last guy, when you say there's simplified trusted operating systems available, what's an example to that?
One example to that would be the virtual vault web server by your package. And there are others who are one pitfall. Also, you mentioned that they have had some trouble to get their own system up and running. This can happen to each and every system.
say that that's simplified in terms of the management. I agree that any system needs to make a screw up. And
Okay, there's now a whole argument going on live.
so I take it outside.
HP virtual vault.
Sorry.
Anyway, I think to put an end to this part, then the configuration problem shouldn't be underestimated as being part of the security problem. And in that sense, the current offer of secure operating systems isn't really sufficient for all needs. And there are interesting new solutions, and that was why the Jill examples available or being thought of, because it's only like half a year old now, that offer alternatives for specific uses, and that's, I think, a key element. You don't want the all-out general purpose solution per se, and that's what the most trusted secure operating system solutions are.
Just a general request, has anybody actually played with the NT rootkit?
If someone actually played with the Windows NT rootkit.
A very small amount.
I just wanted to meet up and see how far they've got. The last time I saw the patches for NT, it was to remove file permission checking, so that you could just access all the files as anybody. It was just a quick patch in the checking code for the file system to say you haven't got permission for that.
I know the rootkit server actually sits on my rack, and normally there's like no activity on that web server. I don't see much activity, but right before the Singapore show, I sent some email to Greg Hoagland saying, hey, what are you doing? There's no traffic on here. The site hasn't been updated in a year. And so he sent out an email to everybody saying, hey, what are we going to do? And next thing I know, there's all kinds of activity on that site. I mean, it's constantly getting a lot of activity. So he said it was pretty amazing on their internal mailing list. As soon as he posted one message, all of a sudden about 8 different people started contributing code again. So it sort of rejuvenated itself in about the last 5 months.
There are other rootkits here as well. I mean, there are other kernel level modifications for NT which are not part of that open source project. So
yeah, and apparently there's a lot of stuff that hasn't made it in the public portion of the CVS repository.
That's basically what I was asking, was sort of how far have they got. We can see process this being Trojan beer and whatever. I just wanted to know how far.
Joey, if you watch Joey's speech from Singapore, he demonstrates an exploit where you can move from user land into kernel mode and basically traverse the whole NT security model, which breaks everything. And so, of course, everybody wants to get the hands on his code, which he just kind of flashes on the screen a little bit. And then, of course, Joey disappears and nobody can get their hands on him. And he moves. He started to work for, I think, Network Associates now.
I think that problem is fixed in Win2K.
Oh, Service Pack.
Service Pack 6 should have fixed it. I think it was a problem in Service Pack 5, but I'm not.
Oh, okay. Yeah, because I mean, he just demonstrated it. So I'm not sure. Anyway, so it looks like there is action going on there again at long last.
Any more questions?
Okay, we're going to take a 15-minute break and then move on to the next session. So you can either storm Job up here or storm the coffee. We'll see you back in about 15 minutes.